Welcome. In this session, we learn how to evaluate the inverse Laplace transform of a function x of s. So if x of s is given, how do we take the inverse Laplace transform of this x of s, right? So in other words, our goal is to find x of t from this x of s. Means x of s is given. How do we find the time domain expression from this x of s? Right. So one of the popular methods in literature is to find the inverse Laplace transform is using partial fraction expansion. So here one popular method is partial fraction expansion method. So let's assume x of s. What we do in partial fraction method actually, let's assume x of s is of this form. Suppose we have terms, we have some expression like here in s, and we have the terms like 1 by sa plus 1 sb, sc, and so on, depending upon the order. So depending upon this order of this x of s, we'll have the terms like this. So what we do in partial fraction method, what we do, we simply write it as a1 by s plus a plus a2 by s plus b and a3 by s plus c. And our goal in partial fraction expansion method is to find a1, a2, and a3. Now, once we find the value of a1, a2, a3, we can write the inverse Laplace transform very easily. So if we are able to find the value of a1, a2, a3, then the inverse Laplace transform, where a1, a2, a3 are referred as residues, by the way. So a1, a2, and a3 are referred as residues. So once we found those value of these residues, what we do, we can write the inverse Laplace transform very easily, because we know the inverse Laplace transform of 1 by s plus a is simply e to the power of minus at u of t. So the inverse Laplace transform becomes very easily, means we can do the find the inverse Laplace transform very easily, right? So if we are able to express x of s in this form, first of all, then we can write the partial fraction expansion, and then we can write the this inverse Laplace transform very easily. So the inverse Laplace transform of this simply will be x of t, which is equal to a1, after we have found the value of a1, e to the power of minus at u of t, plus a2, e to the power of inverse Laplace transform of this term, minus bt u of t, plus a3, e to the power of minus ct u of t, right? So the inverse Laplace transform is very easy to find after that. So this is how we write the inverse Laplace. So the first thing is we express it as a partial fraction expansion, and our goal is to bring it in the form of 1 by s plus a. That's what we do in partial fraction expansion. But we may not have always the terms like this. Sometimes we may have a polynomial that is given in quadratic form, cubic form, or fourth order form. How do we bring it in s plus a, s plus b, and s plus c form? And depending upon the order, we have different expansions, or there's different ways of expanding this partial fraction and this here. Okay, so to illustrate this, what I mean by different cases, let me take one simple case. Let's take an example. Let's take an example here. Suppose we have x of s as simply s plus 1 s into s square plus 5s plus 6, right? So what we have here, we have a cubic polynomial actually here, right? Where s is taken out and then one term is left, that is a second order polynomial in s. Now, how do we express it like this, right? So we find the factors of s square plus 5s plus 6. So if you remember from the basic math classes, how do we write the factors of the quadratic polynomial, we first find the roots of this quadratic polynomial. So if we have a quadratic equation or quadratic polynomial, x square plus bx is equal to c is equal to 0. How do we write the roots? There will be two roots because this is a second order polynomial or equation. The roots will be given by this b plus minus b square under root of b square minus 4ac divided by 2. Right? And let's suppose the roots of this general second order polynomial are the equation are alpha and beta. Then what we can do, we can write this ax square plus bx plus c can be written as simply x minus alpha and x minus beta. So it will be written as x minus alpha and x minus beta as a product of this, right? So we have a quadratic term here. How do I express it in this form? So what we do first, we find the roots of this quadratic polynomial or quadratic equation. So 5s plus 6 equal to 0. What we do? So we say this is a quadratic equation. Then the roots of this will be s1, 2, means s1 and s2 will be equal to minus 5 plus minus. So it will be 25. 5 square is 25 minus 4. A is 1. C is 6. So C is 6 divided by 2a, A is 1. So this will be minus 5 plus minus 25 minus 24 divided by 2. Then this is equal to minus 5 plus minus 1 divided by 2. This is equal to minus 1 plus minus 1 divided by 2. Minus 5 plus minus 2 divided by 1. Then this can be written as minus 5 plus 1 divided by 2 minus 5 minus 1 divided by 2. So it is minus 4 by 2 minus 6 by 2, which is same as minus 2 and minus 3. So then, so the roots are minus 2 and minus 3. That in other words means we can write this simply as, so that in other words means we can write s square plus 5s plus 6 can be written as s minus 2. That will be s plus 2 and s plus 3 product. So it will be equal to the s square plus 5s plus 6. You can express as this. These are referred as factors of this second order polynomial. Okay. So then from the original polynomial x of s, what we have. So from this original polynomial x of s, what we have, x of s is equal to s plus 1 divided by s into s square plus 5s plus 6. This can be now written as s plus 1 divided by s into s plus 2, s plus 3. So we replace it s square plus 5s plus 6 by s plus 2 into s minus s plus 3. Now we can use the partial fraction expansion method. So we can write it as a1 divided by s plus a2 divided by s plus 2 plus a3 divided by s plus 3. Now you can see the roots are here distinct. So the roots of this quadratic polynomial are distinct. We may have the equal roots or the repeated roots. We may have also complex roots depending upon what is this quadratic term in this x of s. So based on that, we have 3 different cases for this. Okay, so this is the case for distinct roots. So we are actually discussing the case when the roots are distinct roots. We have a quadratic term, but the roots of that quadratic term are distinct. All right. So what we do, we write the partial fraction expansion. Now our goal is simply to find value of a1, a2, and a3. Now there are different ways to find the value of a1, a2, and a3. What we do here, we'll simply multiply both sides by this denominator term. So multiplying both sides by this denominator term, once you multiply that, from this term, denominator and numerator will get cancelled. So we'll be left with s plus 1, that will be equal to a1 into, when you multiply both sides by this denominator term, s and s will cancel, so we'll be left with s plus 2 and s plus 3 plus a2. Once you multiply both sides by, throw this term by s into s plus 2, s plus 3, s plus 2 will get cancelled from numerator and denominator, so we'll be left with s into s plus 3 plus a3. And if we multiply both numerator and denominator by this term, s plus 3 and s plus 3 will get cancelled from the numerator and denominator, so we'll be left with s into s plus 2. So this is after we multiply both sides by this. So after you multiply, what we did, multiply both sides by s into s plus 2 and s plus 3, right? So our goal is to find a1, a2, and a3. What we'll do, we'll simply make that two terms 0 and find one of the residues are constants. So if we put s equal to 0 in this, what will happen? This term will be 0 because s is 0. This term will be 0. So we'll be left with only this term, which is non-zero. So that means s is 0, so it will be 0 plus 1. That's equal to a1 times, when s is 0, it will be 2 multiplied by 3. So let me clear this here, screen here. So that means a1 from this is simply 1 by 6. Now to get the value of a2, what we'll do, we'll make s equal to minus 2. So we'll put s equal to minus 2. Once we put s equal to minus 2, so it will be minus 2 plus 1. Now this term will be equal to 0. You can check it. When you put s equal to minus 2 here, this term is 0 here. So it is 0 plus a2, s is minus 2, then it will be minus 2 plus 3, that is equal to 1. So a2 will be simply equal to minus 1 divided by minus 2, that's equal to 1 by 2. So a2 we have found. Now to find a3, we'll put s equal to minus 3. As you can see, when s is equal to minus 3, this is 0, this term is 0, right? So we'll be left with this term only here. So when we put s equal to minus 3, it will be minus 3 plus 1, that's equal to 0 plus 0 plus a3. a3 is minus 3, s is minus 3, so it's minus 3 minus 1, right? S plus 2, when s is equal to minus 3, will be equal to minus 1, so it is minus 2, that's equal to a3 times 3, that means a3 is simply minus 2 by 3. So now we have found the value of a1, a2, and a3. Substitute it back here. So that means, so once we put the value of a1, a2, a3, so a1 is what we have here a1 divided by s plus a2 divided by s plus 2, and a3 s plus 3. That means a1 is 1 by 6 divided by s plus a2 is 1 by 2 divided by s plus 2. a3 is minus 2 by 3, so it will be minus 2 by 3 s plus 3. So once we, now x of s is like this. Now we know the inverse Laplace transform 1 by s plus 2, and 1 by s plus 3. We know the inverse Laplace transform simply is u of t. Inverse Laplace transform of 1 by s plus 2 is simply e to the power of minus 2t u of t, and inverse Laplace transform 1 by s plus 3 is e to the power of minus 3t u of t. So after we write this here, so that means x of t, once we take the inverse Laplace transform on both sides, it will be 1 by 6 u of t plus 1 by 2 e to the power of minus 2t u of t minus 2 by 3 e to the power of minus 3t u of t. So that in other words, x of t we can write as 1 by 6. We'll take u of t as common, e to the power of minus 2t minus 2 by e to the power of minus 3t. And outside we have u of t. That means we can write it like this, right? So this is the inverse Laplace transform of this given function. So what we had a term which is like this. So in short, what we do in what we do, we express as a product of these terms like s plus a, s plus b, and s plus c. Then we write the partial fraction expansion of that x of s. And the inverse Laplace transform. To write the inverse Laplace transform, it becomes very easy. So we can write the inverse Laplace transform very easily, right? So this was the first case. If the roots of this quadratic term are distinct, means we have two different roots of this. Means the roots are not same or complex. In this next session, we'll see if the roots are same or repeated roots. Okay. So let me stop here. In the next session, we'll continue the discussion.